This is a tutorial I've been excited about for months, and I haven't been able to make it until now. Here's what it is. For a while now, we've been wanting physics inside of geometry nodes, not just, using a Geo Nodes thing and then running a physics simulation, but a built-in solver node. Well, I'm done waiting. I made my own. Check this out. Here's Suzanne, and here's Suzanne falling. And this is physically accurate in a sense. You can, change the initial condition, so Suzanne's like this, and Suzanne will fall in a different way. It also works with object scaling and all this. And we could have it drop from higher with a different rotation, and it's all deterministic. And you might think, oh, beautiful, he made a solver node. It's a bit complicated. So here's the node network we're making. Basically, the reason there's this monstrosity is we need to do time steps. We don't have a loop node, so we need to say, go a bit across time, make a calculation for the physics, then again and again and again. And each physics calculation, this is what these groups are, is composed of a couple of steps that I will explain why they work. So this is technically the prompt for Nodevember day 4, which is alley. So I made a tiny bit of a bowling alley looking thing. Again, the point is this render, the physics are all procedural. I know it doesn't have much to do with alley, but I thought you guys would be more interested in how to make physics with math instead of how to make a bowling ball. So let's get started. Do I need to save this? Nah. So as always, take everything, delete it, start off with a new cube, geometry nodes, and add a Geo Nodes group. What I'm going to do is I'm going to break down the idea of a physics simulation into steps that we can do over and over and over again. Starting off, I'm going to start with a mesh. So this is going to be the thing that I want to simulate. And we can hide that, and we are going to import it. So it's all procedural in the sense that the physics are procedural. We do need to import in an object, though. So in our group, our geometry nodes group, I'm going to import in Suzanne, so we can now view it. And this is the only thing that's an import. You can also, by the way, use a primitive and run physics on a sphere or something like this. So I'm going to take my monkey, my Suzanne, and I'm going to bring it up, and I'm going to rotate it a little, maybe on the x-axis. So these are my starting conditions. What I want to do is I want to have this fall and interact with the ground in a bouncy kind of way. We need to break this down into steps. So the first thing that I'm going to do, and here's kind of the game plan, step 1, apply gravity. So it's first going to go down. And it will do that faster and faster as time goes on, because it's a force, it's an acceleration. Gravity is a force. We have acceleration due to gravity, so it's negative 9.8 meters per second squared. So gravity is going to get more and more, intense in a sense. The force is staying the same, but the acceleration makes it look like it's going faster. So first we're going to do gravity. Then we're going to check, has it passed through the ground plane? So once it goes underneath the xy, we need to do something about that. And then we need to have bouncing. So those are the 3 steps. Let's start with gravity. Gravity is pretty simple. We take our initial conditions. So this is our monkey that I've rotated and put up. And we want to move it down. So I'm going to transform, and we want to move it down on the z-axis using some, physics functions. Again, if you don't remember, force due to gravity, acceleration due to gravity is negative 9.8 meters per second squared, which means every second per second, the velocity increases by negative 9.8, downwards every second, right? The velocity is changing. Long story short, what we can do is we can say, I only want to change the z-coordinates since gravity is going directly downwards. This is going to be related to time. For now, I'm just going to use a number for this. So let's say 0.1 seconds have elapsed. Again, it's meters per second squared. So I'm going to, first of all, square this, power of 2, and then multiply by negative 9.8. That's just the gravitational constant on Earth. So you can see before, after, it drops just a little bit. And again, we expect it to drop faster and faster as this continues. So again, we have 0.1 seconds have elapsed, and then we square it times negative 9.8. In fact, what I'm going to do is the next time we're going to say 0.2 seconds have elapsed, then 0.3, 0.4. What I'm going to do is I'm going to take this 0.1 and multiply it by 1, which kind of seems like a weird move. But I want to be able to say 1, 2, 3, 4, and it's going to drop faster and faster and faster. Okay? So we can take all of this and turn it into a group. And this is our gravity. So again, we have our initial conditions, and then we go one step down. And then we're going to go 2 steps down. And 3, 4, 5, 6. And you can see when we preview this, this is our initial state, and then as we play this, you can see it's falling faster and faster and faster. Right? The gap is growing each time. Pot tie break. So in some sense, we have gravity figured out. And again, each one of these blocks represents a time step. We're going to make a switcher that flickers through them all, so we get like, we play through these steps. But you can see this has now passed through the floor. So what we need is a function that says if you pass through the floor, put it back on the floor, since this is our kind of collider in a sense. You could also get more complicated, have a terrain. I'm just going to do a floor. So let's see, we go 1, 2, 3, so far good, 4, 5, still above the ground, 6 we get under. So what we're going to do is, again, each block is representing gravity. I want to say after the gravity step, so we can shift P this to say this is gravity. What I want to do is, again, I want to move it. In this case, we want to move it upwards so it goes back on the floor. I want to move it using this function. What I'm going to do is, you're asking, how do I know how far up I need to go? Well, basically, the algorithm is you look at the lowest point, which is kind of the chin in this case, and you say, how far away are we from the ground plane? That's a distance, and then I say move it up by that distance. So the reason I'm using attribute statistic here is we can take the statistic of the position, specifically the z-coordinate is all we care about, so I'm going to separate by x, y, z. And that's what we're, by the way, I'm going to save this. This is going to be available on Patreon and Gumroad and all this, in case you don't want to make it yourself. We'll call this physics node. So again, we're taking our geometry and we're sampling what is the z-coordinate at each point, and then we want the minimum. Again, that's saying what area is the lowest, the most negative in a sense. And I want to take this and multiply it by -1, because if it's at like -2 meters, I want to shift it up by +2 meters, right? So I flip it by -1, and then I add that to the z component. And by the way, if you're paying very close attention, you'll notice there's going to be a problem here. But first of all, let me connect it. So we do this, and boom, it's on the floor. Now, if you think very carefully, what is the issue with this? Well, it works, gravity and then this, right? We have our 2 steps. By the way, I'm going to take this and put it in its own frame. So this is now the floor step. What is the issue with this? Think about it. Well, let's look. If we start with our initial condition, we now go to step 1. You can see it's immediately on the floor. What happened is it applied gravity, and then it said, oh, you're floating above? Take the negative distance and map it down here. So what I want to say is do this floor thing, like map it back upwards if it falls past the floor. Only do that if it's beneath the XY plane, not if it's above. So it's a conditional thing. So the way we do this is I say, only do this step that we described if the minimum z value is less than, you can do 0.001, I'm just going to do 0. And that's going to give a 0 or 1 true or false value, multiply it. So what does this mean? If the minimum z component, in this case, is positive, right, it's above the thing, this is not less than 0, so it's going to output a 0, and it's going to scale everything by 0, and it's not going to transform. And that's going to be true for here, 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 until it gets under, in which case it is less than 0, and then the -1 multiplier will apply. So, let's see. Initial condition, gravity, 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 and then floor. And you can see, you'd assume the more steps we add, so again, this is the 7th, the 8th step, etc., nothing's going to change, because gravity's pushing it downwards, fine, but also it's going to be on the floor. So the question now is, what do we do to make this look more realistic, right? Because all it's doing is it's just falling. Well, what you'd expect to happen is there would be a bounce at this point, or maybe a rotation, right? It's falling on its chin, I'd expect it to kind of rotate downwards until this section touches the ground, right? That's the next step. Well, this is probably the most complicated step, by the way. The question is, how do we describe the rotation? Which way should it go? Stuff like this. Well, here's what we're going to do. Once it's on the floor, and only if it's on the floor, again, similar to the floor step, only apply it if it's relevant. If this thing is touching the floor, what I want to do is I want this to be the pivot point, so it's going to be rotating off the chin, and it's going to be rotating in, we know it's this direction, but the reason why, intuitively, mathematically, is because this thing has a center of mass, right? It also has a pivot point, and if you look at the direction of this vector, it will show us which way the rotation should go, especially if we take this and map it to the floor. That's going to say which way this model should rotate or lean towards. So again, this step is a bit complicated. What we need to now do is the rotation step. So I'm going to go into the node group. So again, we have gravity. By the way, we can name these to keep it as simple. We have gravity. Let's label this. Is that not how you label? Oh, there we go. We have gravity. We have floor. So you can now see these things have labels. The next step is adding a pivot. So what is a pivot? It's a rotation. You could do another transform, but it's a bit more complicated because if I was just to, let's say I was just to rotate, you could, by the way, it's doing this weird thing because it's doing this like not just once, it's not just rotating. The reason it's bouncing and all this is because it's applying it a bunch of times, so the rotation kind of accumulates in a sense. So don't worry about that now. But you can see the rotation is not like based on any pivot point or any of this. So what I'm going to do for the rotation is we're going to use a set position node, and I'm going to rotate the position using a vector rotate. So instead of using a transform, I'm modifying each point. I'm going to do it the same for each point, but using a vector rotate node. So we want to rotate what? The position. What is the center of rotation? Well, we know it's at the chin. Mathematically, what we want to do is we want to say, hey, look at all the points where the z value is very close to 0, and then take the average position of those. That's what the pivot point is. So in another case, it might be over here if we tilted the object and all this. Mathematically, again, we want to say what areas are close to 0 on the z-axis, find the average position. So let's do that. So a lot of attribute statistics, which is why as the mesh gets more divided and all this, also in normal physics, it gets more complicated. It's more expensive to calculate because you need to do an average of a much larger thing. So I want attribute statistic of, what do we want to sample? We want to sample the position. So I want the average position of this geometry. So by the way, this is actually just the center of mass, what we have right now. So let's actually keep that. We know that's going to be useful. I also want not the center of mass where the average position is. And by the way, center of mass is a bit more complicated. Like some of these points can have weights and stuff like that. We're not going to get into it. You could actually make a physics engine that you make the chin way more and all this. But I want to know what is the average position of only points, a special selection of only points that are satisfying a certain condition. That condition is that the z-coordinate is very close to 0. So what I'm going to do is I'm going to look at the z-coordinate of the position, and I'm going to say which one of these are less than, you don't want to say 0 because you're going to run into a bit of an issue. I'd say 0.01. And the smaller you make this, the more accurate it's going to be. So I'm looking at z values that are very close to 0, anything that's under this line, 0.01. Of that selection, sample the position, and now we have, this would be the mean, would be the center of mass. This would be the center of rotation. So again, we have center of, or pivot point, center of rotation, and center of mass. And we want this vector. Luckily, we know that this vector, pretty simple, is just the subtraction of the two. If you don't know why, it's just some vector math. Don't worry about it. So I'm subtracting their means, because again, the mean is the average in the sense that we want it. And what I want to do is I want to rotate based off all of this. So let's think. What I want to do is I want to rotate the position with the center point, the pivot point, to the center point of the pivot, which we know is this. The axis of rotation, which direction it should rotate in? Well, we want to take this vector, project it down, and then rotate it by 90 degrees. So this is the axis of rotation. So this final vector I just drew is what we want. So we want to kind of rotate across this line. The way we get that is, we have the subtraction vector. We project it to the floor. We rotate it perpendicularly by 90 degrees, and that's our axis of rotation. That's something we can also obtain with a vector rotate node. So the vector I want is the subtracted projection. So I'm going to project it to the xy plane by multiplying by 1, 1 for xy, change nothing, z is equal to 0. I want to take this projection, I want to rotate it off the pivot point on the z-axis by 90 degrees. Bit confusing. We'll see if we made a mistake, and we're going to connect that to the axis. Now, I'm going to do this. You're going to see that it's going to be a bit glitchy. You can see it's kind of doing the right thing, but it's like flickering and all this. Again, this was the same issue we had before. It's doing this on every single step. It should only do this if it satisfies the condition that it's on the floor. Again, how do we calculate if it's on the floor? Well, we already have this thing over here. So I'm going to use another attribute statistic. I'm going to look at the z-coordinate for the entire geometry, and I want to ask, is the minimum, the slowest z value, is it less than, 0.01 or 0.0001, whatever you want. You don't want to get too precise because then you might get rounding errors and all this. So if this is the case, we want to rotate this by, so I'm multiplying this 0, 1 if statement by some angle. So let's see what this does. It looks a bit better. It ain't perfect. So let's see what we got here. So again, we have the floor step. We have the floor step. We have the rotation. And we're saying rotate the position based on the center of the pivot point. Again, that's areas that are less than 0.01. That's the selection. Find the average position. Beautiful. We want to rotate that by the special vector axis, which again is the subtraction of the two. Do we have these flipped? I think we do have these flipped. That was an issue. Now you can see it's doing something a bit more predictable. Still glitchy, but a bit better. So we take this vector, we project it on the floor, and we rotate it. Once it's on the floor, we rotate it by 90 degrees off the z-axis, and that's our axis. And our angle will only apply if this thing's on the floor. Okay. So the issue here, and this is getting pretty good, but the issue here is it's getting glitchy because it does the rotation and then it's below the floor and all this. So what I want to do is I want to do another floor calculation. So again, we have gravity. Check if it's on the floor. Do the pivot point. Let's make this pivot point its own frame as well. Shift P for that. So Shift P. And now I want to cast it back to the floor because it might rotate a bit past the floor. And we can also do a bit of math to fix that. But I'm going to take this floor frame. Can I just duplicate it? No, that just duplicates the frame. I want to take all this, duplicate the entire frame. So again, this is just our little function block that will move this to the floor. We connect this here, we connect this here, we view it, and you can see now it's recasted to the floor. And let's name this thing pivot. So we have our pivot block. Let's see what this does. So again, this number right here, very important, is our rotation amount. And you can see it became a little less glitchy right there. But I think what's happening here is that it lands on the chin, it rotates, then the head, this section right here, hits the floor, and the chin goes up, telling it to now rotate back the other way, and it's kind of in this infinite loop. and it gets kind of crazy. So I think, and this is a thing in physics as well, you'll notice if you don't apply like a dampening or a friction, it kind of gets crazy. But let's see what we have so far. We have this thing on the, like, we can get rid of all this. We have this thing in the sky, it falls, it falls, it falls, it falls, it falls. It goes through the floor, does a bit of rotation, rotates, rotates, and you can see it's actually doing pretty well. I think one thing that we could benefit from, so let's see, let's add a couple more steps. Let's have 13 steps. So this is 9. Again, each one is doing all our 7, 8, 9, 10, 11. Again, each one is doing the whole gravity step, etc., etc. So let's see. It falls, it rotates, 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 and now it's going to kind of forever go back and forth, back and forth, back and forth. And this is, again, a thing that will happen in your physics simulation if you don't apply friction or dampening or something. So the final thing to do is to apply a friction or a dampening or something. So in this group, we don't need to add another block for this. This is more so just a, by the way, this needs to be outputted. Let me make sure that it's still working. Yeah, it's still going to rotate forever, but we want to apply dampening. So at each step, at each sub-step, we want this rotation, this amount of rotating that it's doing, to get weaker and weaker and weaker. So what I'm going to do is, let's think about how we can do this. I want to multiply, let's say each time, let's say our initial rotation is 0.5, for example, which is a lot. What I want to do is I want to take 0.5, and each frame I want to subtract away some amount. So again, we start at 0.5, and we shouldn't go below 0, so I'm going to clamp it. We start at 0.5. At each step, we are going to subtract away, let's say our number is 0.05. I'm taking away 5% of its rotation. And I'm going to multiply it by these numbers I'm putting in here. So 1, and then it's going to get rid of 5%, 10%, 15%, and that number happens to be a group input, so we can use that over here. So again, I'm taking 0.05, this 5% subtraction, and making it bigger and bigger and bigger each time, taking it away from 0.5, and this is how much I want it to rotate by. So let's see what that looks like. And we might need to play with these numbers. And you can make them parameters. So it's falling, 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 rotating, rotating, it's settling, and you can see it's stopped because it's lost its rotational momentum, so it's not going to do the pivot step anymore. Okay. I guess a good thing to do would be to test this. So I'm going to start with a different initial condition. So I'm going to rotate it on its ear, see what it does. So falls, 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 rotates, 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 and then it's going to start settling because I don't want it to go forever. And you could also do this as an energy function over time. I'm not going to mess with that. So I think now kind of the last thing is, assuming that this works, and we could add a collider and all this, my original one that I'll make available somehow, I might sell it or something, has collision. But I think our last step now is we have all these simulation steps, but we have to like flicker through them, right? So what I want to do is I want to make a thing that does that for us. So what I'm going to do is I'm going to use a switch, which goes between two geometry states. So we're going to start with our initial condition, and then step 1, and then this to step 2, this to step 3, and we're going to make a little math time function that says when do we apply these switches. And this is just going to be a way to flicker through these in a way that looks like it's an animation, in the same way that video is a bunch of pictures that play very quickly. We're going to be playing these simulation steps that are deterministic very quickly. So you can see right now, it's all the way at the top, even though we're looking at the final thing. Again, it's based on these switches. So I want to first apply this switch, and then this one, and then this one, and you can see how it's falling faster and faster and faster. What I want to do is I want this to be relative to time. So I'm going to take seconds and multiply them by, right now it's going to be a bit too slow, so I'm going to say let's make time like 15 times faster. I just know that from experience. The switch is a 0 or 1 thing, so I want to say once 1 second, which is really a 15th of a second because of the multiplying by 5, has elapsed, I want to turn on the switch. and I don't want any rounding issues, so I'm going to round down. So it's going to be 0.0, 0.1, 0.2, 0.3, and it's going to be casting down to 0, and only after it's greater than 1, turn on the switch. Similarly, we're going to use another floor function for this. This time we're going to delay, this time we're going to delay time by 1 second. So again, it's only going to do this after the other one. So it's going to do this first, then it can satisfy this condition because it's going to be a second behind. And then let's duplicate this again. For the next switch, we want to subtract by 2. It's very similar to this thing we were doing before with the chaining. So at this point, what I can do is I can just add in a bunch of floors. Once you see the pattern and the connections, you can just kind of copy them. And you could literally just extend this to make this a 30-step simulation or a 40-step simulation. So I'm connecting the floor functions to the switches. I'm then adding in a bunch of subtractions and connecting them. And it's nice. You at some point you can kind of turn your brain off and just be like, oh, I'm just connecting here. There's a pattern, you know, like this. And then we want our multiplication to be in the first socket. So again, don't think about it too much. Just follow the pattern. This is a long tutorial, but we are making physics. If you want me to talk about collisions and all that, let me know. I'm also thinking about doing cloth simulation in here. So again, we delay by 1 second, 2 seconds, 3 seconds. And you can also make a function that puts in these numbers so you don't have to type them yourself. But that gets a bit confusing, I'll admit it. 10, 11, that should be good. So we have 11 subtractions for 12 things. I think that makes sense. So let's see, let's play this. And there you go. You can see, again, as time progresses, and it's going to be 15 times faster, it's going to go through these switches and give us an animation. If I change the initial conditions, it's going to do a different physics simulation. Again, this is something you can totally change the thing of, so let's start off with a cylinder. And some of these might be a bit glitchy, just warning. So I have a cylinder, and it's falling in a way that looks kind of correct. Now you're going to notice that it's kind of stopping when it's still tilted, which it wouldn't do. This is an indicator that our dampening is a little too strong. So instead of 5%, let's say it subtracts 4%. And now we have a cylinder falling in a way that looks very realistic. Let's try to see if it can fall on its side. So I'm going to rotate it in a way where it would definitely fall on its side like this. Yep, there you go. So again, I took this and turned it into a nodevember prompt. I just wanted to show how to make the physics. And yeah, thank you for watching. I will expand on this concept if you want me to. This isn't a bad implementation of geometry node physics. Again, there's other steps you need to do with collisions, with energy, with friction. But you can make a thing, and it plays pretty fast, especially since it's evaluating the entire mesh. You could even get weird with it. Let's see what happens. I just want to see. I haven't done this myself. I'm going to extrude mesh and give it some weird thing. Yep, seems to handle that fine. Whatever, I can go further with this. But either way, as always, I just want to say that this blend file that is very complicated to make is going to be available on Patreon, so you can play with it. Just get the node group. And the one I made has a bit more parameters. You can choose the time step, the speed, the maximum momentum, all this. But you can get it there, or I think I'll also put it on Gumroad. And if you like what I do and want to support what I do, the best way to keep this channel running, free tutorials and all this, is via Patreon. Even $1 a month is huge. Thank you, everybody, for watching, and I hope you learned something. Bye.